what? How do you do that? Well, Gauss thought about numbers a lot, and he was aware of this pattern. So the way you can discover it without induction is like by grouping numbers. You can think about, it's really this with this, this with this, this with that, this with that, this with that. So you've got 11, 11, 11, 11, half the number of total times. So that's 1/2 n times n plus 1. People don't think Gauss was proved it by mathematical induction as a kindergarten. He was a master of patterns. But there's also a story, Gauss was 3. His father, I think, was doing accountant work, or he wasn't. I don't know if he was an accountant or if he was doing accounting work, but he had ledgers out. And when Gauss was 3, he would come up and go that number's wrong. Yeah. Anyway, as you go on in math, you'll hear the name Gauss again and again and again, because Gauss did a stupid amount of things in the 19th century. In all of math, like algebra, number theory, analysis. He discovered non-Euclidean geometry before a lot of other people, but didn't talk about it because it had a lot of philosophical overtones that would have got you in trouble. Like if you say things like Euclidean geometry was wrong, you have the philosophers jumping all over you because it was not people they conflated the Euclidean geometry with physics. In other words, the world has to be Euclidean because that's the only way we can imagine. So when you say that there's non-Euclidean geometry, you're saying that the world isn't the way it is or something, and that was offensive to some people in some sense. And but actually, that's something I labored under for a while as a physics student, thinking that physics was reality. It took me a long time to sort of understand, wait a minute, physics is a model. It's not actually what's real. Maybe it's an approximation to what's real, but that's my personal opinion, is at most an approximation. And it's worse than just that, because that doesn't quite do it justice. As we go on in science, we discover new concepts which sometimes supplant old concepts and make the current way of thinking about things completely bogus. For example, Newtonian time. We have all of these philosophical arguments based on a Newtonian understanding of time. But general relativity has shown us that there's another way of thinking about time. Everything, all of these arguments that we have about linearly ordered in time, what do they mean in light of a way of thinking about time which is much more nuanced and open? I don't think a lot of people really appreciate how incredibly game-changing that is. In physics, we have particles and waves, but who's to say that that's the end of the story? We used to just have atoms, right? Now we have nucleons, and we used to just have nucleons. Now we have quarks, and who knows what else? And sometimes these are just kind of subdivisions of what already exists, right? But this thing about time not being absolute, that's changing not just the characters on the stage, it's changing the rules of the game. I don't know. I am content with physics just being an approximation. For me, it doesn't have to be actual reality. But anyway, I digress, obviously. So this is a finite sum, right? And so let me just explain to you how this has to do anything with the area problem. So we'll end here today, and we'll start here next time. But basically, this is the deal. To understand how to calculate area under a curve, we need to use the concept of a sequence to capture it. And so, you kind of already... Do you remember as a kid ever going into a room and trying to figure out the square feet in the room by counting floor tiles or something? You ever done this? Right? But then what happens if they've got a curved counter in the front, right? Exactly. So we are always limited as children because, like, the size of the tiles is fixed, right? But the basic idea is if we want to calculate the area, say from A to B, under a function y equals f of x, so we want to describe what's this area in here, right? Our goal is to describe that. What we can do is we can chop it up into little rectangles, all right? Just like imagine little skyscrapers, if you will, right? And I'll be boring and make, I'm trying to, I mean, you could make them variable width, right? But trying to make these kind of equal width. And I made my function far too boring. This is almost constant. Dummy. What's that? I don't think I've done this yet. Maybe at the start of class, but so, you know, right. So we're going to take the interval from a less than or equal to x. So a less than or equal to x less than or equal to b. We take this interval and we partition it like this. A equals to x sub naught, less than or equal to x1, less than or equal to, well, not equal to, but less than x1, less than x2, less than xn equal to b, right? And so, like, this is x1. I made it too small. So this is x1. This one would be x3 in my language. Here's x5 over here. X7. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This b would be x10 in my picture, right? So you have basically you have a sequence of points, right? And what's the area of this one? Area of the first one would be like f of a times the width of it, which we'll call delta x. Now delta x will just be b minus a over n. That's the thickness. So if the thickness of the strip is delta x, and the height is given by f of f of a here, right? What's the height of the next one? If I call this thing a2, what's the a2 is what? It's f of x1 times delta x, right? That would be the area of that one, right? And so you can use the height of the function times delta x to give you the area of each rectangle. So approximately, the approximate area would be equal to the sum. I'm using left endpoint, so I do sum I equals 0, all right, to 9 in this case. My picture, here's my picture. Sum I equals 0 to 9 of f of x of I delta x. And I didn't tell you what the formula is for this picture, but that would be, using this. This is using 10 rectangles, right? If instead I had used this is with left endpoints. Left endpoints. That would be approximately the same as if I used the sum I equals 1 to 10 of f of x of I delta x. So that's called a right. So the question is, how do you define the height of the boxes, right? You could use left endpoints. You could use right endpoints. I mean, you got choices. So here, if I start with 1, then these boxes, like, I can't really draw it very well because I made my picture too small, but the other one I'm drawing would be more like this. It's up essentially the same. It just gets shifted over. Like that would be this one. And I think you can see where I'm going with this. So the nth approximation, we could get by the sum I equals, let's use right endpoints because the formula is nicer. I equals 1 to n of f of x sub I delta x, right? Where x sub I is equal to a plus I times delta x, and delta x is b minus a over n. So next class, I will start by like carefully building this stuff up and like going through it again. But this would be the approximation of the area under the curve using n strips, each of width delta x. Right? Now that's going to approximate there. How can we get the area? How can we get it to be exact? What do you want to do? You want to let n go to infinity. If we let n go to infinity, the widths of these get smaller and smaller, it gets to be closer and closer. And so we'll actually define the area under a curve as being the limit as n goes to infinity of an expression like this. That defines the area under a curve. We take the limit of the number of approximating rectangles going to infinity. And you're like, well, how doesn't that, if you're taking the limit of infinitely many things, how is it not blowing up? How is it not going to infinity, right? But the devil's in the details here. Notice that while we're taking, if we're taking, the limit as n goes to infinity of the sum. So this is why I was talking about sequences and limits here today, guys. Is because we need sequences and limits in order to set up this expression, right? That's why I was talking about it. So this is area under the curve. The area bounded by y equals f of x between a less than x less than b. The thing is, yes, n is going to infinity, right? So you're adding together infinitely many things, but at the same time, what's happening to this? Right, it's going to 0. So you're adding together infinitely many things that are infinitely small. There's a balancing act going on here. And it happens in such a way that you end up with something finite. Now, the shocking thing is, this has something to do with antidifferentiation. What does this have to do with antidifferentiation? It's not obvious, right? And this is what separates Newton and Leibniz from all of the greats before them. People were dancing all around it. People had understandings of tangent lines. People have understood this idea of dividing area up into little pieces to like get a finer and finer approximation to it since the ancient times. Archimedes did this, right? Great ancient, mathematicians / physicists have done this sort of infinitesimal calculation for a long, long time. But connecting it to the story of antidifferentiation and the tangent problem and how they're interrelated, that is the thing that Newton and Leibniz understood that people had not understood before. And maybe somebody did it before somewhere, but no one understood it in such a way that they could communicate it to other people and impress upon them that it was something that we should build as a cornerstone of like mathematical analysis going forward. But anyway, so I'm teasing you a little bit, like I haven't shown you the answer yet, but I would just point out that it's really kind of shocking at this point that the start of this lecture has anything to do with the end of it. But we'll see that it does next week. Thanks, guys. Sorry to go long.